Yes, it's just a general overview. Test run. It's not going to be good. Keep in mind that this presentation, it, computers are separated into sort of separate components. Most of the time, the separate components are taught, separate from each other, right? They aren't mixed together. This presentation mixes them together. You understand all aspects of a computer. You want to understand all those aspects well. We skip some of the fundamental stuff, right? We Our entire purpose is to make sure that you understand how this stuff relates to each other, and not even in like all their ways, just to a large or to a sizable degree, you should understand how parts of the computer interact with each other. That means we skip over some of the fundamentals, right? Just so you can understand the interactions, right? By the end of this, you are by no means an expert. You aren't even close to being an expert. You just have a different perspective than if you learn from other people. Let's get started. Hardware software abstraction layers in programming in C, C++, Python. Let's start with this hardware software abstraction layers. Probably one of the most important things I can give to you. Right. It's the perspective I was talking about with those layers, or with those components. We'll see them right now. Okay. Start with programming language. Programming language is how you, uh, or actually, no, let's start with the sort of the three big, the three big bosses of this abstraction layer. It's called abstraction layer. We won't describe, or we won't, you won't fully understand abstraction. Just know whenever I'm referring to hardware abstraction, hardware software abstraction, it's this one. First, you can probably already understand hardware and software, right? The third one I decided to add is physics. Physics is pretty hard. It's very, very meaningful. Uh, can have an impact on everything in this. Most of these can have a sizable enough impact on a lot of the other stuff as well. But physics, you know, is sizable enough to have extreme impact. So, in order to summarize sort of how the three interact with each other, specifically, software is what controls the hardware, right? Software is telling the hardware what to do. Hardware does it, and then hardware has to adhere to the laws of physics. Now, keep in mind, these are not laws that you can break. You won't go to physics jail. You just cannot violate these, right? Uh, if you do violate these, then you are making a mistake. Whatever you're reading from is mistaken, or you are finding like a frontier in physics or something, right? Yeah. Okay. So let's start with programming languages again. Programming languages are in the software category. They are code that you can understand. So you want to tell the computer to do something, and you can understand relatively easily what it is you're doing, right? And operating systems. Operating systems just uh, they handle giving control over to the hardware to some extent. We'll speak more on that. We'll speak more on that later and why that isn't sort of closer to the middle, the hardware and software like this, but it's handling inter- interaction with the hardware, and then it does that with just code in general, but also with like files and other stuff as well. All right, this ASM slash machine code. ASM is just a more readable version of machine code, right? And what machine code is code that the computer can understand. Programming language is how to make code that you can understand. Machine code is code that the machine can understand, right? Okay. So all code all code needs to be turned into machine code, right? That's why it's pretty low. Instruction set architecture. There are a couple. We will discuss this, but there's a couple different instruction set architectures, and they determine how you write or how machine code is created. Um, well, obviously, if you're running two computers that fundamentally just like run differently, right? Like they just do different things in different ways, right? Uh, you cannot write code that the machine can understand for or for computer A and assume that it's just going to work for machine B, right? You need to have some amount of okay, there's going to be compatibility between the two. And if they implement the same instruction set architecture, as in they can do or they have a list of, I don't know, hundreds of things that they can do, and then you tell them to do these things in certain ways, then you can guarantee that the machine code for one is going to work on the other, right? And then so to the rest of these inner workings up to physics is just making the hardware work, right? And it's sort of harder to discuss at this higher level. So I'm just going to say, ooh, it makes the hardware work, and then we'll discuss it later, right? Moving on. Okay, let's talk about programming languages, right? Let's see two right now, C++ and Python. Left is C++, right is Python. We have int num equal to 17, semicolon. And then we have num equal to 17, semicolon. Let's look at some of the differences. Int versus no int, right? We won't discuss that. If you want, or we will discuss that in a later section. Not right now. Num equal to 17, that's fine. Semicolon. Semicolon, all that says is that, okay, we're done with this line. We're done giving you things to do. Move on to the next one. That's what tells the computer. Computer, when it is translating from this code into code that the computer, or then the, yeah, that the computer can understand, right? Mm-hmm. Okay. Num plus equal to 2. Okay, yeah. The second line is num. Uh, okay, so we have that, and num. What is num, right? So like, why do we have that first line, right? Num is a variable. Now, what a variable is a tool to store information, right? So in this case, num is storing the information 17, right? So you're storing the number 17 in num, right? And let's pull on the second line. Num plus equals to 2. What that is doing is that is adding 2 to your value num. So first line, num is 17. Second line, num is 19. What's the third line doing? It says print, and then look closely. It's not saying print num. It's saying print open quote num, close quote num, right? It's print open quote num, close quote num. Now, why is that relevant? You can see it here in this separate example. We have print open quote. This is a single quote, but still, in this specific case, it doesn't matter if it's single or double quote, right? We have print quote the big black box, that text, right? And because we have that quote, the text is shown out, right? If you see, there's only one line there. There's no way that a variable is declared, all right? So whenever we have that quotes, it's just text. And then whenever we have, for example, a situation like this, then the variable would be printed out and you would get 17. Okay. Now, you have to, in a computer, there's a lot of memory. You need to identify where your memory is, and it can be useful. We have these things called memory addresses, right? Now, what is a memory address, right? It's just a place where you store information such as a variable, right? And I'll have 3 for now. Okay, so here we have 17, and 17 is num, right? So we have num. And, okay, num. What is this at, or and, sorry. This is and or ampersand. You'll hear me probably call it ampersand in the future. Ampersand num. What that's doing is saying, okay, we look up num. Num is at this memory location or memory address 1, and we take that memory address 1 and then we have int space star ptr or star pointer. This is what is called a pointer, which is just a variable that has a memory address in it, right? Instead of having a number or, I don't know, a little text string or whatever, it has a memory address. So this pointer is just a variable which will have mem address 1, right? That's all it is. Okay, so that's a pointer. Malik. Okay, this looks pretty big. Don't be worried, it's not really hard. Okay, for first things first, what is this? All we won't be discussing this. I just I left this here mostly so that you notice it, and it's like no, jot it down. We won't be talking about it. You can absolutely learn about this on your own. Okay. Once again, pointer. It's pointer. This time it's called a ARR or array. I'll be calling it array. It's actually called ARR in the code. Get the point. Okay. We won't be talking about this. This is just a little fancy thing to make this this sort of uh, feasible for this. Feasible for this part. I won't go further into detail. You don't understand what's happening right now. That's fine. Google it if you want to. Blah blah blah. Okay. We have this malloc, right? malloc is called a function. What a function is it can either doesn't or does take in some amount of input information, right? Probably a variable, maybe a couple of variables, right? Maybe 0 variables, right? So it takes in input, and it goes through some code, right? So we can have we have this code, and we have some other code, say written over here, and we say, okay, go to this code, go through the steps in that code, hit that, and then come back, and then if you specify so that it does it, it'll give you out a variable, or maybe it'll give you a variable, or maybe it'll give you uh, and maybe it'll give you nothing. But in this case, it does give you some. It does give you a variable, which we'll discuss. Okay. So notice this slash slash is a comment. Basically, you can write annotations in your code. This should be here. That was a mistake on my part. Okay. So you can write annotations in your code, right? Find it in here. Okay. We have this malloc. Basically, what it does is it allocates a form of memory called a heap memory. And what heap memory is it's just general purpose. It's a form of general purpose memory that you can use for whatever you want to use it for, right? So in this case, malloc is saying you're requesting the computer, hey computer, I want to I want uh 5 times size of int worth of memory. Please give it to me, and say where I can access that memory, and then it will return or it'll give you the variable of a pointer, and you take that pointer and you check you check it here. Is that is that the same as null? If it is null, in this specific case, it returns null, and this function only returns null if the memory you requested it was impossible to get for some reason, right? If it does, then we can handle that. Otherwise, okay, we're happy with it. We would interact with our memory. We'd oh yes, we have this memory. We can play with it. Then we have to free it. Eventually, we have to free it. We have requested this memory, and once we're done with it, we need to say, okay, we're done with this memory. Uh, we don't need it no more, right? Okay. So we've talked about variables, memory addresses, and pointers, and malloc, so which is heap memory. Remember, general purpose dynamic memory you can use for whatever. And now we're going to talk about a thing called data structures. Data structures are just a method of structuring variables slash information slash data slash genome. Okay, so let's look at that first example. It's called an array. So an array is multiple related variables just put into one data structure, right? So in our examples, we have int my underscore nums, and then we have 1, 2, 3, 4, and then the Python version is slightly different in how you write it, but also notice that comment. in Python, multiple different types of arrays that you can have, and we are only showing you one. It's called a list, but remember, or just keep in mind, this is only one type of array. There are others in Python. And then we go down, and then we have what's called an associative array. Associative array is, well, it's another it's another collection of related variables. However, we are we are treating uh, our collection as pairs of variables, right? So we are looking and we're saying, okay, we pair up. We say we have Alice, which is a name. So we have a name, and then we could have, let's say, an age. So Alice is 30 years old, and we pair that name and age together into one entry in our associative array. And in Python, that's called a dictionary. And in C++, it's called a map, right? And you can see the sort of differences and how they go, right? Okay. So it's important to know, right? We've been talking about code. Code's written on files, right? These are code snippets, but like we here, this one here, that's a file, right? That's a file. So code's written on files, and files, not only they do have code, right? Not only do they have code, not only do they have important code, like code that makes up your operating system. Keep in mind your operating system is very essential to having the running of your computer. Not only do they have that, not only do they do stuff like just general purpose code, they also like store images, store uh, video, store I forget what it's called, audio, just stuff like that. They store a lot, right? They generally store of pretty big amount, relatively high amounts of information, right? So you'll see a file, and let's say it's called like sonic.exe, right? There's two parts to sonic.exe that we care about, right? Okay, there's this first part and there's the second part, right? First part is called the file name, the name. Second part is called the file extension. File name, how you identify a file, right? It's a name. File extension is a little bit more important though. File extension is what you're suggesting to the computer that the file is for. In this case, it's called an exe, sonic.exe, right? Sonic.exe is to the computer, it's thinking, this is probably going to be a file that will be run as code, right? Like this is the version of the code that the computer can understand. We talked about it before. It's called machine code, right? So this is probably machine code. And then let's say we have another one dot file dot py or a Python file, right? Once again, this is a file name, file extension, right? So Python file is code written in Python, and then it's called a file. All fine and dandy, right? Now, just because we have the file extension .py doesn't mean that we have to have Python code, right? We can have a grocery list. Like we can cheese, milk, eggs. I don't think I don't think all of this, right, which is a valid Python code, it doesn't exactly look like cheese, milk, eggs, bananas, rice, right? Like this just doesn't look like valid Python code, and it isn't, right? It's not valid Python code, so yeah. But that doesn't mean that the file has to contain, right? It has to contain valid Python code. It can contain stuff like this. The file extension is a suggestion. Now, keep in mind, whenever we're running files, right? Like we're making our computer interact with files in some way. Uh, the files or just the format of your file, like is it a Python file? Is it a C++ file? Is it a exe? Is it a audio file? Those matter, right? Because they're formatted in certain ways, and your computer needs to needs to be able to handle those certain formats. So what does it do? It uses a system where files there's files split up to header called a file header contents. All right. Okay. Header has what's called magic numbers, right? So magic numbers is just some form of identification. In a Windows exe, for example, exe has 4D5A. Those some awfully great numbers, I know. We'll explain how magic numbers can have 4D and 5A in it later, but magic numbers. And then as the contents, right? Now, exe is a special exception to this header and contents because the contents are split up in ways we'll discuss later, but okay. And then, for example, for this here, we can see this dump, and then we can see this is a JPEG file, and then it has the JFIF header, which indicates to the computer that this is a JPEG file. Mm. Okay. Yeah, and then sort of an example of interpreting a header is whenever you run your computer, or whenever you run code on your computer, right? It'll read the header, and it'll recognize it's an exe, and then it'll treat it like machine code instead of treating it like, for example, if it's an audio file, it'll treat it like information, right? So that's just like one thing. And keep in mind, it runs it on the CPU. CPU is the part of your computer that is running code. That's all it is. CPU part of your computer running code, and the exe would run on the CPU. It would, yeah. Okay. So we move on, and let's talk about how we can interact with files in code, right? Because, yeah, we can. So we look at the first part with open a underscore file, and we're reading it. And then we go to the second one is with open file that doesn't currently exist in the file system, and well, it doesn't exist in the file system, and we're writing to it, right? Like, how are we supposed to write to a file that doesn't exist? Well, what happens for Python at least is that the file will be created. It'll be created with the writing, and then yeah, it's written to. And then we have the third one is we open a file and we write to it. Mm? Okay. We've talked about how the operating system handles like what code is run on your exe and just like files in general. So yeah, let's just talk about how the file sort of works here. Um, but before we do that, we need to understand something: is that the OS is not, or not, all parts of the operating system do not have full control of your computer in the way that the kernel does, because the kernel can execute privileged operations such as issuing IO, which is file stuff, and executing all types of restriction instructions, right? Okay, that's what the kernel can do. Kernel is the guy orchestrating with your computer to do stuff, right? The kernel is that guy. The rest of your operating system, the rest of your computer, does not have that power. So, for example, we have these programs right here, right? We're writing the code, running the code, running the code, and we read it, right? And it goes through a library routine, right? And that library routine is a function, right? It's a function, and that function hits a syscall, something called a system call or a syscall. And what happens is the syscall indicates to the computer that okay, you're running in this called user mode. User mode is outside of the kernel. It doesn't have full access to talk to the hardware in the way that the kernel does. And we say, okay, we want to do something that only the kernel can do. only the kernel can interact with, only the kernel can play with files. So please computer, I want to interact with files. Go to the kernel, tell it I want to do this thing, and then the kernel will do it on our behalf, right? So once again, we have our program. It's a library routine. That library routine is a function. So it runs through the code of that function, hits a system call, and then it's in kernel mode, and then it can do what it needs to do, right? So what does it need, or how does the file stuff work in kernel mode, right? Okay, first things first, we request a underscore file, right? So, and then in order to understand it, we need to draw out our CPU diagram. Okay, so right now, just RAM, and this is called disk memory. This is where the files are stored. This is called a solid state disk. This is disk memory, right? CPU. So you run an exe on the CPU, right? It's running, running, and we hit a syscall, and that syscall switches us from user mode, and then the syscall switches us to kernel mode. And then the kernel is now running on the CPU. The kernel needs to make a request to the SSD through, I forget what this is called. I think this is the interface or something like that. It makes a request to the interface what we need again, right? So it needs to know, okay, what what's called logical address do I give to the SSD so it knows what file I'm referring to, right? So it needs to do that. Then it needs to know another thing. It needs to make sure the at least the kernel needs to make sure that you're not accessing top secret documents or whatever, right? It needs to make sure of that, right? So there's two so first it needs to get the instruction, the necessary logical address. Second, it needs to make sure that you have perms, right? Make sure that you're not accessing these top secret documents. What is the third thing? It needs to do a third thing as well. That third thing is it needs to translate that logical address into something that can be transmitted, right? It needs to, uh, there is hardware involved that does not, that will not immediately understand logical address. Like you can't just tell it logical address. You need to shape it. You need to shape your information. You need to make it understand, right? You make it understand by giving the information in a certain way, and you do that through something called a driver, right? So, for three things that you do. You first get the logical address, you check the permissions to make sure that you can do stuff with it, and then you need to translate it into some way that can be sent to the that can be sent over to the SSD so it can do stuff, right? Okay, so how does it do that? So first, it goes through something called a logical file system, which contains file metadata, the sort of patterns on the folders or slash directories. Folders and directories are the same thing. And then it has power over file creation as well. In the logical file system, it goes to the part of itself where it stores metadata, which is just information about files, such as the permission and the logical address. It finds the logical address in the file organization manager, which is the library, or sorry, it gives our file name, and then we look it up in File Organization Manager, and we get the file control block of our respective file name, right? It's okay. Now we have that. In the logical file system, we check the permission, right? Yes, sir. Is the permission good or is the permission bad, right? We get the permission, and then now we have the logical Uh, so we have the logical address, we have a permission, we need to translate it using a driver, right? We use the basic file system and IO control to translate it, and then we can send it off to the disk via a physical I forget exactly what it's called, but physical connection called NVMe or SATA or SATA or NVMe, right? Okay. And then okay, those off. SSD receives the request from a controller, right? The controller takes in the request. Okay, fine and dandy. Then it has to hit something called a flash translation layer. Okay, flash translation layer. That's it, right? Sort of, that name sort of maybe starts making you think, how does SSD work? First things first, right? There's a couple different parts of the SSD. There's this here, this controller, and the FTL flash translation layer. Then the part that stores all the memory called NAND flash, right? NAND flash stores it in what's called flash memory. That type of flash memory is a NAND. Alright, it's NAND, right? Now it's in NAND flash. Or sorry, now it needs to get to NAND flash. Now there's a couple. Now it needs to first go through this flash translation layer so that the logical address, right? The logical address can be translated into a logical block address. So basically, the place that the address for the operating system needs to be translated to the address of the flash, right? And then there's a couple of reasons why that happens. We'll talk about it. We'll talk about at least one of them, right? And in order to understand that, let's have this here. This is what is called a block. And block is made up of pages, so we'll have B1. And we'll split that up into pages. Then we have B2. Right. This is page 1, page 2, page 3. You got the point. Right. So just the flash translation layer, it's keeping track of all this stuff, right? All these blocks. So for now, all of these are invalid, right? Invalid, invalid, invalid. Like the information here does not mean anything. It's not good information. We should not be caring about this information, right? Okay. We don't care about this information. It's not good information. How do we remove it? We erase it. Okay. So we erase. Right. So okay, we erased this. Now we want to write to something, right? Like, okay, we have erased. Now we want to write. Okay. So we can write to just one of these pages, and then it gets set to valid, and then let's say we write the value of a here. Okay, notice the difference between erasing and writing. Erasing, we erased an entire block. Writing, we only wrote to a page. Why does that matter, right? Let's say we have A, and then we write B, then we have C here, right? Now, let's say we want to update A, right? So we want to do that. Or I should probably set these all to valid as well, because they are valid. Okay, let's say we want to update this with the value of, let's say this A with this little symbol here to say that it's the updated value. Okay. Or actually, I was spoiling it. Okay. Remember, when we erase, right, we erase an entire block. So in order to update this value of A, we would have to completely erase B and C and store them in another location, right? That's time consuming, that's annoying, or that's just inefficient. So Instead, we would write to this thing A here, right? And then all of a sudden, the flash, the logical address and the logical block address are different because A stops going, or A is no longer thought of as going here. It's now pointing at the updated value, right? So the uh, the FTL would look up A at P4 at page 4, B at page 2, at page 3, right? Okay, so theoretically, right? Let's say we write, I don't know, let's say we update A prime again, or A again. Okay, now we've updated this. Or, oh, we have to, okay, first we have to erase. I forgot that these are all invalid. My apologies. Okay, all this becomes erased, and then we start writing to it, right? Okay, all this is erased. We start writing it. Let's say we update B, C, and then, okay, let's just have a new value D, right? Okay, first off, the FTL, it completely erases this as P5, right? And then goes to P6, P8, right? Okay, notice how none of these are pointed to by the FTL. All of these variables are here, and all there are being written to, but none of them are actually like accurate. So a process called garbage collection would come in and hit all of these and remove them because they're taking up space that can be used by other stuff. I'm just gonna not rewrite this as valid, but you get the point. And then this one would become erased, 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 and then yeah. Okay, so the flash translation layer. Once the controller gets the logical block, it's translated through the flash, and then it gets what it needs to do. It writes what it needs to write, and then that is whatever whatever file or whatever you need is updated or is sent to RAM over a process or over this is called DMA or direct memory uh, arrangement. I forget what it's called. Okay, DMA, and DMA would go something like this. So we're here and then okay. Once it is in RAM, uh, our kernel is over. Like kernel is done. So we return to user mode and then user is done, right? So that's pretty much how a file interaction would look. It's not super complicated. Yeah. Okay. Okay. So all in fine and dandy, we looked at the files. We looked at our files. Uh, there's one thing though. Here, for example, we looked at JFIF, and if you do actually look up JFIF, it is 4A46, right? Let's look this up for, yeah, 4A46. 4A46, 4, or no, it's 4A46, 4946, right? How is that JFIF, right? If the actual computer, or at least if this representation of what the actual computer sees is needs to be decoded into decoded text so we can see JFIF, what's happening, right? Well, the process of representing just some information, so say a number or a letter, right, with some other form, right? So in this case, we're representing uh, letters with numbers, letters with numbers, well, numbers and letters, but yeah, we're representing uh, numbers with numbers and letters, and that's called encoding, right? So you can encode information just like, okay, uh, I want to have my representation, or you can say, just like I want to represent one thing with another thing, or you can say, okay, I want to write a number in a certain way. So what a certain way would be is, for example, if I want to write the number 3 in base 10, I would write it 3, right? Base 10. You're used to writing in base 10. Guess what? You can change the base of your number. And for example, here, in a single digit, I can write 0 to 9, right? 0 to 9. What happens if we reduce the base, right? Then the number of digits we can represent in one place value decreases. So here's 10, so we can write 0 to 9, which is 10 digits. In base 2, we would be able to represent only with 0 and 1, right? 0 and 1. So in order to write that same 3, for example, we would have to write uh, 1 as our first place value. And then, well, this is just 1, it's not 3, right? So we would to add this additional 1. And then in order to sort of understand the logic here, it's like, how does this work? Okay, you can think of it like this, right? So we have the value 54. Now, this place value, in the place value, the digit is 5. But because the it's in the tenths place, it would be 5 times 10, which is 50 plus 4 is equal to 54, right? Here, sort of the same way. Uh, Here, this is in the or I don't know what place it is, in the seconds place, right? So we have 1 times 2 plus 1, which equals 3, right? And in this way, we can write numbers in different bases, depending on what's suitable, right? So we have base 10, base 2, and then the base we saw is called base 16. So, oh wait, how were we supposed to write 16 place values or in just one digit or in a single digit, right? We can't have 16 be our place value, right? So what people came up with is they would say, okay, you go 0 to 9, then you go dot, or then you would continue by going A to F, and where A represents 10, and then F represents 15, and then the letters in between represent the numbers in between. You get the point. So if we want to say 15, if we want to represent the number 15 in base 16, we would write F, right? And that's where that came up with, or came from. hmm And then this is what is called an ASCII table. ASCII is a very popular, or pretty popular form of encoding just a number with a letter, right? And then you want another example of ASCII. We have this capital T is 54. Then you'd look it up. Where is capital E, capital D? And we see, yes, it's 5, 4. So yeah,